Swayam Prabha. Digital India. Educated India.
Welcome back, guys. So here we are talking about alcohols. Okay, well, some of you are above 21, but for all the others, we're going to talk about alcohols and all the crazy things it's going to do to you. Just kidding. We're going to talk about alcohols in general. And alcohols that we call alcohol is just one molecule out of like a million. So alcohols, what's the special thing about them is they have an OH inside. That's the main thing about alcohol, an OH. In fact, 2/3 of your diet is packed with alcohol. 2/3 of the food you eat, because carbohydrates are packed with alcohols. So the alcohol that you think does crazy things to you is just one molecule. That's the culprit here that goes into your brain, and it's like a little drug that makes you do crazy things for some time. So that's your beverage or drink. Drinking, when you go out drinking, that's the one that you're going to consume. You're eating a whole bunch of this alcohols every day, like your carbohydrates, carbon with water, carbohydrate, carbon with water, carbohydrate, carbon with water, OH and H. This is what you're eating all the time. Unfortunately, you don't get high on this, CH2OH. So that's your food, that's your glucose, this is carbohydrate. So that's how important this functional group is, about 2/3 of your diet. Why? Because OH is kind of like water. H2O also has an OH. And so it can dissolve in it. What's the point of eating something that's not going to dissolve in water, right? You can't really absorb it, you can't digest it. It's going to go through like a block. But here, because you have hydroxyls, they can get absorbed into your body, go into your blood, soluble. So that's how important alcohol is. One, it's already oxidized, and then it can get oxidized further and release a lot of energy. So you kind of get a high. It's going to be soluble and can be transported to your brain and anywhere you need energy. So it's a really, really, very important functional group. Your life pretty much depends on it, right? On not this alcohol, this alcohol. All right, let's talk about what's so special about it. First of all, let's talk about some properties. So if you have one carbon, it's going to be methanol. If you have just hydrogens. If you have an R group, then it's going to be a primary alcohol, just like your primary alkyl halides. Remember, primary, secondary, tertiary, same deal here with the alcohols. Secondary and tertiary, are they different? Yes, they are. Let's look at the pK values. There's also another alcohol which is a little different. We call it phenol because it doesn't behave really like the other alcohols. Let's look at the pKa values. The pKa is about 10, which means it's quite acidic. Your toilet bowl cleaner has got phenols in it, and that's enough to take off your calcium and all the other deposits. It's slightly acidic. But when you come to methanol, all these are neutral. They're about the same as water. Water is about 15.7, and so this is about 15.9, about 16, and 17, and 18. It could be 16.1, 16.2. So why is it that the pKa is increasing? That means it's getting less and less acidic. So acidity is going to go in this direction. Why is that? Two reasons. One, it has to do with hydrogen bonding. The second is going to be the R groups on here, because that's the only difference between these two, is the R group. So here you have 1, here you have 2, and here you have 3. So they have all 3 donor groups. R groups, carbon, hydrogen, these can give electron density. These are donors. R is a donor. they spread electron density through hyperconjugation and inductive effect. So and we always said acidity is always proportional to the stability of the conjugate base. Acidity of Hx is proportional to x minus or conjugate base stability. And so let's look at the conjugate base and see why. So each of them puts out a proton. You're going to get a minus. So here's CH3. Hydrogens are no good at donating electrons. Are CH2CO minus, R2CHO minus, and R3CO. So here you have 3 hydrogens. Here you have an R group, 2 R groups donating, 3 R groups donating. When you put electron density into something that's already got electron density, they're going to be kind of butting heads, okay? So this is unstable. So donor groups destabilize anion. You want things that pull the electron density off and spread it on that molecule, like here. For example, if you take off that hydrogen, you're going to get an anion, and this anion is pretty happy. It's going to go into this ring and start partying with all these pi bonds. So it's really happy anion. So that's why it's so acidic. The hydrogen is going to just pop off and do whatever it's going to do. So therefore, acidity, this is more stable because there are things pulling that anion, spreading it. Here, anion is getting pushed into an anion, right? 2 same charges. So this is destabilizing. So therefore, the more R groups you have, the lower the acidity. Now, if you have electron withdrawing groups, that's really good. For example, if you take this and instead of putting CH3, let's say you have CF3, CH2O minus, now this is very stable. And the pKa really, really drops for the CF3, CF2OH. Now, the other thing is solid boiling point. They're both tied together. That depends on hydrogen bonding. For example, if you take alkane, this is a minus 89 when you have a hydrogen. When you have a chlorine, it's about 12. And if you put an OH, it kind of jumps through the roof and goes to 78. If you have 2 OHs, then you know 100 degrees centigrade. So you can see that just putting an OH is really going to increase the boiling point so much. The more hydrogen bonding you have, the higher the solubility in aqueous and the higher boiling point. You can see that this is going to then hydrogen bond to another alcohol and another one. So you have a lot of hydrogen bonding. So solubility in water and boiling point are kind of closely related. And you can see these don't have hydrogen bonding, right? Even though this is chlorine's quite polar. And these are gases because they're less than room temperatures. Another property is, well, when you put the acidity of these things has to do with also the reaction. So you can take off the hydrogen with a base. So let's say you bring in a base like this, it's going to pull these off. And it's going to give you an alkoxide. And this is how you make a lot of the alkoxides for reactions. So you'll have your hydrogen come off. Because it's a gas, this is going to be driven forward. Sometimes in lab, when you make your E2 bases like ethoxide, you take this and you put sodium into this. The sodium is going to give those electrons to the hydrogen and then kick them off. So your sodium here, so you will get the exact same thing. And here you will have to have 2 of them because you need 2 of this to get up into the atmosphere as hydrogen gas. So this is just reacting on that acidic hydrogen. What about reacting in the whole of OH? Can I do this? Can I take this OH and substitute that with another group? Let's say I bring in my usual nucleophiles, iodide, bromide, whatever that is. Can I do a nice backside kick? And do you think I'm going to get this at all? What do you think? Well, remember the pKa story? pKa is all you need to check to see if a reaction goes or not for the most part. This is pKa is going to be about 16. HI has a pKa about -9. So this is a way better leaving group. So it's not going to happen in this direction. It's going to happen in this direction. It's going to go all the way here. Look at the pKa. That's all you need to know to see which direction it goes. Lower pKa, better leaving group. So this is going to go backwards. So no SN2 on alcohols the way they are. So we got to convert this to something else. Why do we want to do that? Because alcohols are so cheap. All your trees keep, spitting off alcohols all night. So you can get a ton of those, all kinds of alcohols. So that's a very good source. Unfortunately, you can't do any of the reactions, no E2, no SN2, so what's the point? So what we do is we take this alcohol, which has a very bad leaving group, OH, bad girl, no leaving group, bad leaving group, and we convert it to something that is a good leaving, like OTS, or chloride, or bromide. Now you can do all your SN2s and E2s, and it's just one step. So let's look at how we can convert our alcohols to good leaving group. So the story is from bad girl to good girl, from bad leaving group to good leaving group. Let's do alcohols and see how we can do that. So there are lots of ways. Let's start converting them first to halides, ROH to RX. What is it that we can do to do that? Lot. And depends on whether your alcohol is primary, secondary, or tertiary. If your alcohol is primary, there are three major ways. This is your primary alcohol, and you are going to put something to convert it to an acid. An acid is already an HX, so let's say HCl. So this is something you've seen before. Exact same thing. You protonate that, and then you want to take it off. But the thing is, primary doesn't want to come off and give you primary carbocation. So this is something that is going to be not a very good scenario for this, and this is going to be very slow. So primary, slow, and it's also going to, have other kind of reactions, E1 and so on. So you're not really going to be, not a very good reaction. It's going to get mixtures. So let's see how you can convert an ROH to an RX primary without mixtures. One, this one also is not that great, but it's still better than this. You put in something that makes it an even better leaving group than this. This is water, pKa of leaving group is less than 2, so that's a good leaving group. But you can make it an even better leaving group. We can put something here that's actually going to grab those electrons and make it very, very electron deficient and pull that out of the oxygen. So here is a Lewis acid. So it's called a Lucas reagent as well. You might do this actually one day in lab whenever you get there. So here's your chloride that got kicked out, and well, you lost a lone pair, so 6 minus 5 is a +1. And now your chloride comes back and bites back. Here's your chloride lone pair hitting that and kicking this off. So here's your chloride, and you have zinc leaving with your hydroxide and chloride. So this is a little better and faster than this. Here's something even better than that. You can take the same primary. In this case, you can take primary or secondary, but not tertiary. And you can put in something that's again going to make it into a superb leaving group, something that has very, very electron deficient leaving group. So this is a group. In this case, bromine wants to leave with an octet, so therefore all these bromines are fighting for those electrons to leave, and so they want some help from the oxygen to set that off. You are going to have a positive charge. Now, Some books have it with the pyridine, some books have it without the pyridine. If you put pyridine, pyridine is just a base. It's a very stinky base, but it does a good job of pulling out protons. If they have pyridine, you can take off that hydrogen and you will get your leaving group. If the pyridine is a liquid, so it's also the solvent. Now you can take that bromide that came off and then take that bromide and attack. The bromide wants to then form that bond. This is a good leaving group. Once it leaves, it's not going to come back and go in the opposite direction. So that's something to be mindful of whenever you have reactions with leaving groups. You don't want the products to reverse the reaction, like here. So you want to have a stable leaving group, which is why we're doing all this fancy stuff to that. Now the oxygen OPBr minus. So here is your pyridine. Your pyridine becomes now a pyridinium because you put the hydrogen on there, you took off your lone pair, so you have a positive nitrogen, which is going to then go with the negative that's coming off here, Br. Here is now this alkyl halide. Now you know bromide is one of the best leaving groups. Now you can take this and do all your SN2, E2 and all those very stereospecific selective reactions using this. Whereas this kind of just lies around. It's a solvent really, it doesn't react. The reason why we use alcohol as a solvent is because they're pretty much neutral like water. Let's see how we can do this in another way. All right. This is also for primary and secondary, more than secondary actually. So I'm going to put this arrow because this is an SN2, and so for SN2 you don't want to have a secondary or tertiary. Tertiary is not going to happen. So tertiary, no. And this one in particular, you can actually take this off and have a carbocation if it's tertiary. So this can happen on primary, secondary, and tertiary. Now let's look at another one. Well, you can have a different OH, don't have to have the same one. And here we're going to use SOCl2, and we drew the Lewis structure for this. We know SOCl2 is like this, it's a tetrahedron. So you can have backside attack, you can attack that sulfur, kick out that chlorine, and it's going to come in pyridine. So pyridine is going to be your solvent. Same guy. When you have these hydrogens that you need to pull off, pyridine is like a good sponge. It goes off and pulls off those hydrogen and keeps it there. So now you have pK. So here you have a hydrogen here that's still on there, and that's why the pyridine is needed to remove that. So here is your sulfur. Now you kicked off one chlorine, and so you are going to have that hanging around somewhere in the pyridine. Now this is then going to have deprotonation by the pyridine. So the pyridine comes in, and well, pyridine is a sponge. It's guy with the vacuum, sponges out all your protons, positive hydrogens, and so now you're going to get that neutral. So now you're going to get your oxygen and neutral, and you'll have your sulfur and your chloride here. This is really what we're looking for. This is a nice intermediate, a sulfonyl chloride ester here. And so now this one has a very good, you can see it's very electronegative, it's itching to go. Excellent leaving group. So that's our purpose. Put the SOCl2, turn that bad group into a good leaving group. Now you don't want to be stuck with the sulfonyl chloride. What can you do with it, right? Not much. So you take the chloride, and the chloride is going to hammer it here and push this off. So I am going to have to draw the chloride here, and the anion is going to attack and do an SN2. If it is on a secondary, then you will have an inversion. So because it's SN2. Inversion on if it's chiral. Now you would get your bad leaving group off and replaced with a good leaving group. And the nice thing about using SOCl2, you can do it right here, is this oxygen is going to come and go back to your sulfur, and that is going to kick out your chloride. So you get SO2 there, which is a gas. And what's the good thing about having a gas? I mean, for molecules, okay? What's the good thing about having gas? Is the gas is going to go up and create a lot of positive entropy, which is only going to drive this reaction in the forward direction. You're not going to be able to take that gas and put it back and go in the reverse. So it's just like 100%. Once you hit this, you're gone. It's going to drive the reaction forward, and the chloride comes off. And well, somebody's got to kind of keep this nitrogen here that is positive, have a counter ion. And so that's what happens. This is going to be a counter ion to this chloride. So that's your positive and your negative salt that precipitates, gas goes off, and you get this very nice chloride. This is a very common reaction that you do. So these are three very nice ways in converting a bad leaving group, which is readily available, to a good leaving group, which is like a halogen. These are all primaries and secondaries. What about tertiary? Well, this one's tertiary. What about tertiary? Well, if you have tertiary, when you have a carbocation, you can have rearrangements, and so you can get mixtures. But if you have a tertiary, you're already there, you reached it. Why do you need to do anything else? Let's say I have a tertiary RX like this, OH, and I want to put an OH there. I'm just going to put an acid, HI. And so this is going to get protonated here. Same story. This is just, taking off your OH, bad leaving group. You protonate it, you drop the pKa. Now it's a much better leaving group. And we've done this so many times. And you have your I minus. Here, no SN2. But you can have SN1. This can come out. So no SN2 because it's tertiary. So you do SN1. So you get a positive charge here, and your I minus hammers that, and you get SN1, putting that iodide right there. And in this case, let's say this was a chiral molecule, then you will get up and down. Let's say I have a methyl here that's going to turn this into a chiral, then you would get iodide up and iodide down, just like in your regular SN1. So iodide up and iodide down. Now, if you don't have a chiral center, it doesn't really matter whether you have the iodide up or not because it's a chiral. All right, so those are the ways in which we can take a bad leaving group and convert it to a good leaving group. Now, I didn't do naming, so next time when I come in, remind me to do the naming. All right, guys, so I will see you soon. Bye.